Okay, thanks everyone for joining yet another seminar. Sorry we missed one last week, but there was all the exciting things happening at the Simons Foundation for Global Categorical Symmetries. And as a makeup, we'll also have David speaking next week. So there's a lot of fun stuff lined up. But for today, we have Xingyang Yu, who will speak to us about SymTrees and multi-sector QFTs and the very exciting paper that I just released with a group here on the slide. So yeah, take it away whenever you're ready.
Yeah. Okay. Thank you, Justin, and thanks for the invitation to give me the chance to give a talk for our recent paper. So this talk is based on the work I've just finished with all these authors, with Farham, Jonathan, Max, Ethan, and Andrew. Yeah, okay. So the way I'm gonna arrange this talk is based on these orders. So first, I will give a very brief review of the symmetry TFTs, which is a D+1. Generically speaking, it's a D+1 dimensional topological field theory, which capture the global symmetry structure of a D-dimensional QFTs. And then I will focus on a certain infinite class of QFTs, which admit engineering from a string theory setup. And then I will discuss how the symmetry, then I will discuss how the symmetry TFTs for these QFTs can be engineered or just directly derived from string theory, and how all kinds of defects or symmetry operators can be seen from string theory by various types of branes, etc. After finishing this background review, I will go to some new stuff, which to show that there is actually a very natural generalization of the symmetry TFT notion, which when you consider multiple singularities in string theory or multiple local sectors, which you can engineer different quantum field theories, which admit a decoupling limit, but you can still talk about a symmetry, something like a symmetry TFT picture, but this time it's for a multi-sector QFTs, which we call it SymTrees. So it's like a tree built by several symmetry TFT slabs. And then I will cover some examples to show this is actually doable and has a very concrete actions and setup, which you can play the game to building SymTrees and see what's the global symmetry structure look like in that things. And if time permitting, I will go to some applications in the larger and averaging subject to see how this symmetry picture can have a very nice application in this case. Okay, so let's start with SymTFTs. I guess most of you in the audience must know maybe some or very familiar with this story, so I will give a very brief discussion here. So SymTFT is basically, you can think of it as usually a Q-dimensional QFT. It has some rich structure of global symmetries, and because of the topological nature of global symmetries from the modern perspective, thanks to the work by Cyberg, Gaeto et al., we know that global symmetries is actually, global symmetry G is actually corresponding to topological operators. So due to this topological nature of global symmetries, it is very natural to think of, is there any topological field theory capture this topological nature of global symmetries for my QFT? And the answer is just a one-dimensional higher topological field theory, which nowadays is usually referred to as symmetry TFT. But I want to say is that this is a very popular way to say these things, symmetry TFT in these days, but it can be traced back to like very old work by these people in 90s, when they talk about how you can think of 2D CFT or 2D topological field theory from some 3D bulk perspective. That's like the symmetry TFT idea is quite old, actually. So in the symmetry TFT picture, what you have is you're thinking to extend a D-dimensional QFT you're interested in into a one-dimensional higher bulk. Okay, so you have a physics, and then in this symmetry TFT block, you have two boundaries. One is a gapped boundary, and the other one is gapless, or I mean, usually it's gapless. Let's say it's a boundary physics and boundary topological. Okay, B physics and B top. Here you have local informations of your interested D-dimensional QFT. Okay, you have, by saying local information, I mean under the, usually when we refer to a QFT, we mean that we need some spectrum of operators, and we also need correlation functions as observables between those operators. When we say local information, I mean spectrum of local operators and correlation functions between them. So this is sometimes also referred to as relative quantum field theory. The other boundary is some gapped boundary. And at this boundary, you have some directly boundary conditions for some bulk fields in the D-dimensional symmetry TFT. Okay, this is D plus 1 dimensional TFT. And then you can think of that, oh, I just do a very honest dimensional reduction to shrinking the slab. You will end up with your interested D-dimensional QFT with a certain structure of global symmetries you are interested in. This can be written in terms of as a TFT quantization thing, like you can write boundary conditions, or you can write boundaries of TFT at some, brow cat state in Hilbert space. So there is a notion you can say that, oh, after shrinking the slab, I end up with a well-defined partition function, or I end up with an absolute quantum field theory. Okay, in the symmetry TFT picture, you can very easily to see how the charged defect operator and topological symmetry operator interplay. The charged defect operator is the one going, is the one like connecting between the physical boundary and the topological boundary. And the symmetry operator, in this sense, is the operator which linking with this operator. Okay, so it's something like if you consider a horizontal, oriented operator, which is actually the defect in this case, and the one which is, vertical oriented, it's like the symmetry operator. And then after you do the shrinking, okay, you kill one of the dimension of the defect operator, right? This direction is not there anymore, so it becomes some. Yeah, if it's a small d plus 1 dimensional defect after shrinking the slab, it will become small d dimensional. But the dimensionality of the symmetry operator is not changed. So you still have the linking between these two things in d-dimensional spacetime. Okay. So a very, my favorite example to stress this symmetry TFT is, let's see, 4D n equal to 4, SU2, supreme muse. Okay, here I write this weird SU means that I only specify V algebra for you. So it's a relative theory. I don't tell you which line operator I want to, which spectrum of the genuine line operator I want to talk about now. So it's just a Lie algebra, which I can specify. And the 5D symmetry TFT in this case, written in terms of the differential form, it's a B2-DC2. I mean, you can also write it in terms of the Zn valued, 2 here. You can also write it into Z2 valued cochains if you like, by changing variables and use cup product. But let me just use differential homology here. Let me just use a differential form here. Okay. Then we can say that, oh, at the physical boundary, I have this relative supreme muse, relative QFT, and I can pick my favorite Dirichlet boundary condition on topological boundary so that I specify the global form or global structure of this 40 gauge theory. Let's say if I pick the boundary condition, which is Dirichlet boundary condition for B2 and Neumann boundary condition for C2. This actually leads to SU2 gauge group. So I specify the global form of the theory for you. Why this is the case? Because in this 5D TFT, I can write surface operators like this. I can write electric surface operator and magnetic surface operator. That's staring at these two kinds of surface operator. I mean, you can also have some Ionic version of this thing, like, you know, PB2 plus QC2 or something like that. But let's just focus on this simple case. When I say that I have directly boundary condition of B2, I means that I just fix or frozen the field profile. I don't let it fluctuate on a gapped boundary, which means this surface operator, when attaching in this direction, get trivialized by this boundary. So it can terminate on the boundary. It cannot continue on the boundary, okay? So that's which makes this operator defect in this boundary condition. And if you're staring at this boundary condition, you're staring at this surface operator, C2 is free, so it can, you know, fluctuating along the boundary. So it can, you can make a surface operator here. Wherever you put this surface operator, it will never be trivialized. So you cannot kill the dimensionality of this operator. So this is the symmetry operator. This is the defect. And then you can play the game another way around. I say that, oh, I can pick C2 equal to 0, B2 is free, then this will be defect, and this will be surface operator. And then you know my top line is actually defect, right? And the surface comes from electric field B2, it's my symmetry operator. That's the case when I have SO3 plus global form of my n equal to 4 supermills. And then in the case of Z2, there's a third choice, say that, oh, I can consider B2 plus C2 as the Ionic line. I pick the boundary condition for those things. Then you can end up with SO3 minus global form. Okay, so this is in this simple example how you see from the symmetry TFT and the boundary condition structure about how I can capture the global form or global structure of the of my D-dimensional QFTs and its, you know, topological nature of the global symmetries, all kinds of things. Any questions at this point? Great. Okay, let's go to let's take a step back without thinking global symmetries so far. So let's talk about something about how I can engineer QFT in string theory. Okay, so the motivation here is that, okay, I know global symmetries, which can be captured by SymTFT, which is very nice because we know global symmetries are very powerful. We can use global symmetries to extract some information without doing really some, you know, correlation functions computation, which make your hands really dirty. I mean, of course, if you have some Lagrangian theory and you can write down all kinds of operator spectrum you want, and you can compute correlation functions, you do the S-metric expansion, all kinds of things, you can extract some information you want. But there are some strongly coupled regime of the theory, or the theory is even non-Lagrangian. In that case, global symmetries can be very, very powerful because that's the only information you have. But even only with those global symmetry information, you can extract many, many interesting structures or learn many things from those kind of very hard to handle QFTs. And string theory actually provide a very large stage to engineer this kind of strongly coupled non-Lagrangian theory, especially for dimension higher than 4. Okay, so even if you want to say that, oh, I'm interested in some very hard to handle QFTs, I mean, global symmetry is one powerful tool. String theory is another. They're not just disconnected with each other, but there are some different perspectives. You can try to capture information or capture some knowledge for the strongly coupled QFTs. That's why we're also interested in how string theory can teach us on, you know, infinite class of QFTs. So this is why now I want to talk about how to engineer QFTs from string theory. Usually it's called top-down approach versus to the, you know, bottom-up approach, which you can just do purely field theoretic thing. The setup is like this. In string theory, usually we start with a higher dimensional supergravity or even quantum gravity theory. In 10-dimensional, for various string theories, and it's 11-dimensional for M theory. Okay, so what I'm gonna say is that you can try to split the dimensions of the 10D or 11D string theory or M theory setup with the space-time you are interested in to engineer your favorite QFTs, and the dimensions which are captured by internal geometry. So what I'm saying is something like this. This is let's say I'm still interested in D-dimensional QFT. So this is D minus, R D minus 1, 1 in Minkowski's signature. And sometimes, usually this is not, direct product, but it's more like a fibered structure, but it's not that matters here. And here I have some internal geometry, which had some singularities or which has a localized, okay. So today I will just focus on localized singularity. Okay, it's some singular geometry, which has the singularity here. So times internal dimensional manifold X. So X is, 10 minus D-dimensional in string theory or 11 minus D-dimensional in M theory. And this is the asymptotic boundary of the singular geometry. So this is saying that if I have a 10-dimensional string theory spacetime, I want to talk about some 4-dimensional QFT, then I think of some singular geometry, which is 6-dimensional. And the interesting thing, or there has been like many works on this string theory and high energy theorists have done this like for decades. You can build a very nice picture or correspondence between the D-dimensional QFT and the geometry, which means the geometric information you can capture from this internal geometry manifold tells you many things about this QFT. Tells you maybe if the theory is Lagrangian, it may tell you that what's the Lagrangian is. If the theory is not Lagrangian, it can still tell you like what's the gauge symmetry, what is the matter content, what is the interaction look like. Okay. And there are two properties or two constraints I want to mention here. So what kind of geometry we like? We want it to be non-compact because we're starting with the gravity theory. I mean, the full string theory is a quantum gravity theory, but we are usually, when we say QFT, we usually means QFT decoupled from gravity. It's like some gauge theory or it's some conformal field theory. So we need the internal geometry to be non-compact to decouple the gravity from the bulk. So then this D-dimensional theory is gravity-free theory. The other constraints we want we need this geometry to have some special holonomic. Okay? This means...
Can I ask a question here?
Yes.
So since the internal geometry is non-compact, what sets the scale of, getting a QFT really in D dimensions?
Sorry, what do you mean?
So normally when you compactify, you take some compact internal space and its size sets the mass for excitations, which are sort of non-local from the D-dimensional point of view.
Yes. Yeah, here is the same thing. When I take non-compact, I mean like the G Newton, it's something like, the volume of the internal space. So when I take non-compact case, I take the volume goes to infinity, so I totally decouple the gravity because G Newton goes to 0. I guess the case you are seeing is that you start with some D-dimensional QFT from the first place, right? it had some gauge coupling, let's say something like that. And then I do compactification. And then the lower dimensional gauge coupling is determined by, 1 over the volume times the original higher dimensional gauge coupling. So in
For example, yeah.
Yeah, right. So in string theory, our starting point is just a G Newton or some some gravitational coupling. And then you take the large volume limit, you just decouple the gravity. The gauge theory sector or the QFT sector is not from some non-scale in the string theory. I mean, yeah, in string theory, you don't, at the first place, you don't have other scale. You just have the G Newton or Planck scale from that.
So, but I'm wondering about the dimension of the theory that you get in the end. So I guess it's because you have some kind of asymptotic boundary of a certain dimension that you get D-dimensions.
You mean the dimension of this theory?
Like why separate these two spaces in a product if they're both non?
It's something like so the x is more like something like this. So here I have the r direction from r equal to 0. This is r equal to 0. From r goes to infinity. So what I'm really thinking is that I have some singular geometry, which asymptotically is a conical singularity. And I engineer my QFT just localized on the singularity, which means I only need to take care of the local degrees of freedom in string theory around this singularity. And all the bulk degrees of freedom are decoupled.
I see. Thank you.
Yeah. Yeah, sorry. This picture may be a little bit misleading, but yeah. You can think of that if I have a picture, which is, this is just for the, internal geometry, right? And then I say that, oh, at this point, at the original point, I have a singularity. And then this is just to become the radial shell. And then I just localized, and then I'm just focusing on the singular. I just focus on the geometry information around the singularity, and all kinds of open strings, attaching the singularity gives me what the QFT is localized on this thing. And then the transverse direction of this internal geometry is the D-dimensional QFT. It is the D-dimensional spacetime which I engineer my QFT. But from the internal geometry point of view, it's just localized on the singularity. Yeah. Thank you for asking. Yeah, so the special holonomy means I want some supersymmetry. Okay, because it's, the system is more controllable. It has very nice properties, which is very easy to deal with for computation or some other things. Okay. And this thing, you can do this basically for any dimensionality you want. There are different examples for QFT engineered from string theory in any dimension, like from 1, 2, 3, 4, 5, 6. Just yeah. So that's something you can do. Any questions at this part? Okay, great. Okay, yeah, I think I need to go faster. So let's talk about, based on this QFT from string theory setup, how do I extract the SymTFTs for that QFT engineered from string theory? Okay, this is some name I can remind myself. Have been working on this top-down approach to SymTFTs from maybe last 2 years. I'm sorry if I missed some names, but you can just look into, just type these names in in the Inspire and check their papers and references there. Okay, so you can start saying that, okay, great. In the internal geometry, I see that I have some singularity here. And then at r equal to 0, this is like this. At r equal to infinity, this is my asymptotic boundary. And then what you can do is you see that I start with 10-dimensional or 11-dimensional supergravity action. I do a dimensional reduction along the asymptotic boundary of this thing, okay? Because, you know, this is the radial direction, and we know that this radial direction is just, you can think of this partial x is like growing, you know, along the radial direction, right? And then you think that, oh, I want to do the dimensional reduction on the asymptotic boundary of this thing. Then you will have some picture like this. Yes, you just kill the, you know, the transfer direction for the radial directions. You do this thing. There are some technical subtlety here when you do this for 10D or 11D supergravity, but that's something in principle you can do. And you only focus on the topological sector of the result. Okay, I mean, you know that I start with some 11 or 10D dynamical or physical system. It's some supergravity action, and then I do dimensional reduction. Of course, what's left is not just topological sector, but we can only focus on the topological sector because that's what we're interested in. After doing this, in the internal geometry picture, you have something like this. We already know that localized on this singularity, we have our favorite QFTs. And here we have, by doing this reduction, you also need, and here we have our asymptotic boundaries, right? So I can say that, oh, but I also need to pick boundary conditions, right? I mean, after doing this, I end up with a topological field theory. And the boundary condition for different supergravity fluxes or fields on a asymptotic boundary at arc infinity in the TFT, in low dimensional TFT point of view now, becomes the gapped boundary condition here. If I expand this picture in the space-time dimension, I know that here I have a D-dimensional QFT. Then you have something like this. You reproduce the SymTFT slab picture from doing dimensional reduction on the asymptotic boundary of the internal geometry. I mean, we can do a very easy dimension counting, right? Let's see, I want to do a D equal to 4 QFT. So the dimension, you know, the dimension, sorry. So which means that X is some 6-dimensional stuff. That's great. And then I do dimensional reduction on this 5-dimensional thing, which I will end up with some 5-dimensional TFT. This 5-dimensional TFT is actually the symmetry TFT for my D equal to 4 QFT at the first place. So in this sense, the QFT localized on the singularity is a relative QFT because I haven't specified the boundary condition of all kinds of fields or flux for you in string theory. After I specify all the boundary conditions for you, and then do the dimensional reduction along the transverse directions or asymptotic boundaries of the internal geometry, I end up exactly the symmetry TFT picture for the QFT in string theory I'm interested in. Then it's clear, or it's more or less clear, where can I find the defect and the symmetry operators in this setup. The defect is, I still start with this singularity, asymptotic boundary. This is my asymptotic boundary. The defect is actually the branes which wrapping on some cycles at asymptotic boundary as also as well as the cycles on the radial direction, or it's just radial on the, it's just wrapping the cone over the cycles at infinity. So this is my defect. Okay, because this direction, you see, because this is r equals 0, this is r equals 0, r at infinity. You know, this cycles is non-compact, right? It's like infinite long. So the tension of these branes will be like infinite. That's make it heavy defect in the QFT localized on the singularity. And what is the brane serving as the symmetry operator? It's the brane wrapping on the cycles here, wrapping at infinity. Because these branes are at infinity, so they are infinitely far away from the singularity, only topological effect of these branes are left over. It doesn't have any physical or propagating degrees of freedom affect my local QFT. So the branes wrapping at infinity cycles are symmetry operators, and they are linking with the defect branes. So if I have a defect brane wrapping a one cycle at infinity, then my symmetry brane will be wrapping on d-2 cycles at infinity, and they're linking. And if you do the reduction as I did in the last page, what you will have is this. After you do dimensional reduction, you get rid of all degrees or all propagating or all physical degrees of freedom, only left over with topological field theory degrees of freedom, which means now your symmetry operator brane is now allowed to be pulled into the bulk, because now it's a TFT bulk. It's not a supergravity bulk. So by doing this, I reproduce the defect and symmetry operator in SymTFT slab by doing branes. Sorry, by checking branes, okay? Of course, there are some technical subtle here. You need to make sure which flux in supergravity corresponding to which type of D branes. And then you look at the topological sector of the brane, which is dominated by its West domino terms and all kinds of things. But conceptually, this is how things work. Any questions? Great. Now let's go to, yes.
Actually, yeah. So I have one question.
Yeah.
How do you? I mean, this is maybe if this is too vague or too technical, one or the other, then feel free to skip it. But like, so how do you? Is there a way to systematically control what the SymTFT that you get out is going to be based on? I mean, in principle there is, but is there a way to like? Do we have a handle on it at the level of like, if I said, oh, can you engineer for me the toric code, could you tell me, oh, you put this internal geometry, etc.? Or
it's usually is another way around. So you give me string theory background and you give me the internal geometry, some Clavier manifold you want to talk about. Then I can by hand say, okay, this is how I compute symmetry TFT for you. But I'm not sure if you just give me toric code whether I can do that from. I mean, I'm not sure which internal geometry. Yeah, backwards is a little bit hard. Yeah.
In principle, it's doable. I would.
In principle, it's
guess,
doable. Yes, in principle, it's doable. So in my recent single author paper, I engineered a 3D Z2 to the cube digraph Witten theory from a certain Clavier fourfold in type 2B. But yes, but in general, it's just a. Yeah, I think in general, is people will start with their favorite Clavier or favorite internal geometry and then compute what the TFT is. Generically speaking, the TFT will not be as simple as Z2 toric code or those things like that. Yeah, it might have because there are many others sectors or maybe many other fields. But indeed, there will be always be some generalized version of 3D or 5D discrete gauge theory there waiting for you. And technically, you can do that step by step if you know what your string theory start with and what's the internal geometry you start with.
Can't you obtain the toric code from compactification of the 6D theory. Like, there are papers that people obtain Chern-Simons, definitely abelian Chern-Simons, whose bilinear form for anyons corresponds to the intersection form of the three-manifold they compactify for.
Three-dimensional Tori code, you mean from 6D TFT or from 6?
No, I mean, I just 2D Tori code, which is described by 2+1D Chern-Simons.
Yes, I know, yes.
Yeah, you can.
I thought those are all unimodular, so no anyons.
No, there are. No. For
Sorry.
sure.
When you see when you see 2D Tori code, I mean you're thinking a theory like this, right?
Yes.
You are thinking this theory, I mean, in the continuum quantum field theory language, right?
Yes.
A Z2 gate theory in 2+1D.
Exactly.
Yes, you can indeed have this. I don't know. If you start with a 6D QFT, whose symmetry TFT is 7D theory, it's 7D, let's say Z2 gate theory, then you can do some dimensional reduction, which end up with 3D gate theory.
That's what that's what I'm telling. I mean, it's not it. I just wanted to emphasize that it is known already how you obtain
yes, right, yes,
the Tori code, for example.
Yes, right, yeah, you can, yes, you can do that, yes. Okay, great, yes. So, yes, thanks for the comments.
And
okay, yes.
actually you can, allegedly you should be able to obtain any MTC, like a Chern-Simons describing any rational MTC from 11D compactification, like compactifying 11D theory. But this is less.
The thing is that you do that yes, you can engineer those simple theory as part of the dimensional reduction from 11D or 10D. Usually, if you really do dimensional reduction of 10D or 11D, you will have lots of terms. Maybe some term corresponding to 2+1D Tori code, but that's usually not just those terms. What I would say is hard to get Tori code. I mean, it's hard to just get Tori code after doing the dimensional reduction. There are all kinds of fluxes floating around. If you say that, okay, I only turn on one kind of deep brain flux and I turn off any other flux and then do the dimensional reduction, yes, then maybe possible you can have some as simple as D2 Tori code theory. But generically speaking, generically speaking, it's not as the theory cannot be as simple as that. I guess that's my point. But yes, if you start with a 7D TFT, I mean, if you start with a field theory setup, right? You start with 7D TFT, which is Z2 gate theory, or I don't know, some Chern-Simons theory, and then you compactify on some very simple 4 cycles or 3 cycles, then yes, then you can just get Z2 Tori code. But your starting point at the 7D TFT is already, if you want to embed those 7D TFT into a 10D or 11D setup, you already make the assumption.
Why would I do that? I mean, why would I do that?
Yeah, I understand. No, not much. I'm just trying to say that from field theory perspective, the answer is yes. But if you ask me, can I get Tori code from 10D or 11D supergravity? I would say it's usually the theory cannot be as simple as that. Yeah. Any other question? Okay, great. Okay, so there's actually 2 ways to think how to, I mean, 2 perspectives, think how to generalize the symmetry TFT picture into symmetries. You can, as a bottom person, you can think that, oh, maybe, there are some ways I can build some crazy configuration of symmetry TFTs. But I will now take another perspective because for me, it's more natural why symmetries arise from string theory perspective. What I have told you that, I just want a localized singularity. And engineer QFTs based on the local degrees of freedom around that singularity. And then I build a SymTFT for you by doing dimensional reduction on the boundary of the non-singular geometry. But nobody tells me that there can only be one singularity in string theory. I can think of some very crazy internal non-compact geometry which has multiple singularities. And I want the distance between these two singularities, very far away from each other, so that below certain energy scale, the connected local correlators between these two sectors, or like something like this, like O1, the connected correlators under some certain limit, I don't know, under some mass scale or some other limit of some parameters goes to 0. I say that these two sectors admit a decoupling limit. Intuitively speaking, you can just think of that I have a string theory. My internal geometry is quite crazy. It has two singularities, and that two singularities are very far away from each other. So at local degrees of freedom or local information of these two theories, they don't talk to each other. So I have two isolated relative quantum field theories. But whatever you do, there is a real or genuine infinity for these two things, right? Now I can do similar thing as I do the symmetry TFT from string theory. I can say that, oh, look at this picture. I can do dimensional reduction along this. That will give me a SymTFT, which work in this region. I can do dimensional reduction on this. I can also do dimensional reduction on this in the UV region, right? This will give you a picture like this. After you do the reduction, okay, after doing this, shrinking the asymptotic boundary directions, you end up with something like quite singular. But this is because you do this dimensional reduction, okay? In the previous, in this picture, there's no singularity here. I'm okay. I should draw something like. So there is no singularity here, okay? The only two singularities are here. It's because you do dimensional reduction along different positions, you find this picture. This is like, and then I can take back my D-dimensional space-time into it. Sorry, I'm not sure whether I can draw this picture. Very nice, but bear me for a while. I hope I draw it correctly. Okay. So now I have two relative QFTs whose local information are decoupled here and here. And I have a gapped boundary condition, which is determined by the boundary at infinity for various string theory flux or supergravity fields. And I have a junction operator living here. And this junction is usually not topological. But in every D+1 dimensional bulk, it's a SymTFT. In every D+1 dimensional bulk, I'm doing exactly the same thing as before. I'm doing dimensional reduction of supergravity sector. Okay, I do dimensional reduction here. I do dimensional reduction here. I do dimensional reduction here. I have three SymTFT. Yes.
So just so I understand the geometry here. So the three circles you just drew, the manifold between them is a bordism. Is it smooth?
Oh, you mean this and this?
Yeah.
Yeah, they have to they have to satisfy some matching conditions on this point.
So that point is singular in the space-time.
No, it's not singular. Yeah, that's
Okay.
what I want to
So
stress
it is a
here.
vortism.
Yes, right. There is no singularity
Okay.
here. The only two singularities are here. Yeah, I think I should. Okay. Another way you can think of how this picture look like is a pair of pants. So it's a vortism, as you want. Yeah. It's not really singular. If you look at this picture, it looks singular, but it's because I get rid of the transverse internal dimensions, but it's not. It has to be smooth. It like the field configuration or field profile for various field in the TFT slab, it has to match on this junction.
So you mean that in the D-dimensional QFT, just so I understand, in the D-dimensional QFT, you do have this singularity. It looks like what you drew with the 3 sheets, for instance.
In the D-dimensional QFT, in the D-dimensional QFT, there's no singularity, right? You just have D-dimensional relative theory 1, D-dimensional relative theory 2, a junction theory, which is also D-dimensional, and you have a D-dimensional gapped boundary. Yeah, they're just
Okay.
And this is the same TFT slab for theory 1. This is the TFT slab for theory 2. And these two SymTFT meet at a junction. And this junction also connecting another SymTFT slab. And this SymTFT slab have a genuine gapped boundary condition here.
I think, sorry, can you just confirm for me? I think I'm getting confused. So in your page, let's say the second picture, the middle picture,
yeah,
just because that one's easiest, you have all this auxiliary white space around the picture. But like, I shouldn't actually think that I'm somehow able to like squish these two legs together, right? Because like, do you kind of see what I'm saying? Like, it's not like this picture is existing inside some auxiliary space. I can't like squish them down and then think of it as being like theory T1 theory, you know what I mean? Like on the first star, there's theory T1, essentially. On the second star, there's theory T2.
Yeah.
And I shouldn't think about it like, I'm engineering T1 direct sum T2, right? Because like I can't just fold them down and have them live.
No, you're not engineering
right.
T1 direct sum T2. I mean,
right.
they are direct sum only when you want local information. I mean, if you say that there are two relative theories, then it's direct sum. But they are topological.
Why not direct product?
No, they're not, because these two theories are topologically coupled to each other, right? There is
sure, but direct product over the TQFT,
Okay, yes, sure. Yeah.
Cool.
Yes. If you want to see, okay, yes.
Okay, I see.
Yeah.
Okay, okay.
Yeah, it's something like yeah, sure.
No, you can please.
No, yeah, I mean, please go ahead, I guess.
I was just going to say, can you, I don't know if this is even a thing you can do, but can you control where the singularities are? Can you cause them to collide and then see what happens to?
Yes, exactly. Yes.
Okay.
That will be in my example. Yes.
Oh, okay. Sorry. Thank you.
Yeah, sure. No problem. Yeah. So then you can think of have this picture as the, a generalization of SymTFT, which we call SymTrees. Not symmetry, but SymTrees. It's like an interesting name. And then you can think of some kind of what kind of properties or some interesting configurations you can talk about in the symmetry picture. Okay, I will just talk about something very easy as how the defect might look like. In this picture, you can have some defect which go like this. Okay, if you have a defect go from this relative QFT boundary, and when it goes through the junction, it will be dressed by some localized dynamical degrees freedom on the junction. Or you can have something like this. You can have a defect go here. You can have a defect, and then the defect go here. And maybe this defect can also go here. So you can have defect connecting two different theory sectors. And there are all kinds of other interesting configuration you can play with, and in string theory, we can find both. All these cases actually exist. Yeah, I think it will be better I just skip to the example so that we have a more controllable illustration. So M theory on C2 mod Z1 plus Z2. Okay, so this is a singularity. It's a codimension 4 singularity. So you put M theory on this localized singularity, you engineer a 70 anchored 1 super theory with the algebra SU N1 plus N2. Very nice. And this singularity has a expression in terms of coordinates, complex coordinates, which is plus, I guess, Z N1 plus N2. Now you have this picture. This is S3 mod Z N1 plus N2. Okay, so S3 mod this, or S3 mod this thing is the asymptotic boundary of this. Okay, and then at this point, what do you engineer? You engineer a SU N1 plus N2 theory. For simplicity, let's pick electric polarization. I mean, SU N1 plus N2 gauge group, okay? But now I can think of a complex, I can think of a deformation of this singularity. What do I mean? I mean, I have Z minus T1, Z minus T2, which means at T1 and T2, I have two singularities now. And I can make T1 and T2, you know, I can tune T1 and T2 to make these two positions very, very far away from each other. What do I have? Okay, so this is S3 mod ZN1. This is S3 mod ZN2. But at UV, like very, very far away from the singularities, it still look like they are together. When I go to, you know, very large radio shell, I still have S3 mod ZN1 plus ZN2. Or you can think of in type 2A picture, I have N1 D6 branes, N2 D6 branes. My starting point is N1 and 2 D6 branes. It's a single stack. So I have SU N1 plus N2 7-dimensional supermuse. Then I can say that, oh, I want to split. I have N1 D6 branes, N2 D6 branes. I make these two stacks very, very far away from each other. This is corresponding to adjoint Higgsing, right? I start with SU N1 plus N2 theory. I start with SU N1 plus SU N2 theory. I go to I go to S of U N1 times U N2, which is SU N1 times SU N2 with a U1 factor mod the largest common multiplier of N1 and 2. So now the symmetry picture becomes for the scale below the distance between these two singularities, right? I can see that I sequester these two singularities as doing this deformation of the singularity at the first place. Below the energy scale, captured by 1 over the distance between these two singularities, I end up with this symmetry picture. Because below that energy scale, I'm doing adjoint Higgsing and get rid of all kinds of higher dimensional and get rid of the, you know, the massive W boson and integral over all kinds of higher dimensional operators, it look like I have a SUN1 sector. It look like I have an SUN1 theory and a SUN2 theory along this symmetry picture. But at the real infinity, or in the real UV region, you know your geometry, the boundary is actually S3 mod ZN1 plus ZN2. And here, you have a localized U1 7D vector multiplet. Where does this U1 come from? It's this U1. Or another way you can see this is by doing some very technical thing, right? Because I know the geometry. I know the geometry here is what? The geometry here is just a disjoint union of SU mod ZN1 and SU ZN2. So I just do, okay, I do the dimensional reduction on this cycle. I do dimensional reduction on this cycle. Then this is just a 2 SymTFT slab. And then in this region, I know the symptotic boundary is just S3 mod ZN1 plus ZN2. But along this thing, what do you have? Along this thing, the geometry is S3 mod ZN1, S3 mod ZN1, joint S3 mod ZN2 along the S2. Or you can do something like you can, along the S1, along the half vibration of this thing. Okay, you can compute the cohomology, you can compute the homology group in different region. Then you will know, then you will realize that along the junction here, the topology like this, I mean, these two length space, they are connected or they're gluing along the half fiber. There is a free S2, which is a free P1. You can wrapping on that. And the M2 brane wrapping on that P1 give you the local dynamical degrees of freedom, which corresponding to a U1 vector multiplet. So this is where the gapless degrees of freedom on the junction come from. From the field theory perspective, it's just the U1 factor in the hadron Higgsing. And then you can do similar things again in various dimensions in more and more complicated geometry. It's like it's always easy to do in this region and in this region, okay, because you know what the geometry is. But along the junction, you need to be very careful how the different circles are glued together and become, how the different asymptotic boundary for local sectors are glued together so that you end up with the asymptotic boundary at real infinity. There's some technical details here, but that's something you can do by reading the homology cycles along this junction. You will know what kind of gapless degrees of freedom are on the junction. And these slabs are just a very easy thing. You just do what I told before. You just do dimensional reduction along the symptotic boundaries for different sectors. And then you can, then you can see this thing. So this is the case when I have local sectors, which can be recombined into a big UV theory. There are some more trivial cases. You can start with some singularities which they're not come from a big UV theory. I mean, because usually if you have different singularities, if you want to put them together, sometimes these colliding singularities are at infinite distance in the moduli space, or intuitively speaking, not every, it's like if you give me an arbitrary set of singularities which sequestered from each other, I'm not sure whether they can be combined into a well-defined new singularity at the first place. So in those cases, the junction degrees of freedom are usually not L squared normalizable, but log normalizable, so it will become something more like the Neumann boundary condition for some flux, instead of really some localized propagating degrees of freedom on D-dimensional junction. Yeah, I guess I don't have time to go to this application, but yeah, that's basically all I want to say on this symmetry picture for today.
Okay. Thanks for the nice talk, I guess.
Yeah, sure. Thanks.
It's very instructive. Do people have further questions or comments? Okay, well, while people are thinking, I have one, although it's so it comes back to sort of the previous question I asked was sort of part one, which was about, okay, can you engineer particular TFTs? And now I thought I saw, I mean, maybe it was just in a paper, or maybe I misunderstood, but I thought I understood that, if you have some sort of 2+1 DTFT that you've engineered by picking some particular internal geometry, that like things about the internal geometry then control properties of the 2+1 DTFT. And I thought I saw at some point that like the symmetry group of the 2+1 DTFT was controlled by like the mapping class group of the internal geometry. Is that correct? Or is there some statement like that somehow? I mean, I thought I'd seen this somewhere. I mean, let me make a different question. Let me say it differently. If I gave you some geometric, like some geometric construction, and I told you, okay, I give you this internal manifold, and you tell me, oh, it produces this 2+1 DTFT. Do you know which data of the internal geometry gives, for example, the symmetry group of the 2+1 DTFT, like the braided autoequivalences?
I think is the it's the cohomology group for the internal geometry. So usually, okay, let's say something like this. So I start with a 10D spacetime, and I see that, oh, I want it to be, a 2-dimensional QFT with some 8-dimensional internal space Y.
Yeah.
And I do dimensional reduction on this 7-dimensional thing, right? So my 3D TFT is just 3D times partial Y. I'm doing dimensional reduction like this. I need to go over this thing. So the thing control what kind of 3D gauge theory or discrete gauge theory you have.
Yep.
Is the cohomology class of this one. Which I will just write a simple example, I guess. The H upper 4 of this thing. Let's say if it's D2, then you put for D3 brane, for a P brane, it's a P+1 dimensional spacetime, right? For D3 brane, it corresponding to the C4 field in supergravity, and then you do a differential cohomology at 5. I mean, different. Yeah, it's a little bit subtle, but that's the way how you deal with the torsional cycles or torsional generators in this case. So you put at 5, and you do the expansion because this is the the fourth order of differential. Sorry, the fourth order cohomology group, right? So you can write a generator as T4 for this thing, and this is corresponding to torsional 3 cycles. You do this kind of expansion. So the way to think of this is that in supergravity or in string theory, I have various flux or fields. I want to expand those fields in terms of internal geometry cohomology generators. And after I do that expansion, I can then integrate over the internal geometry cycles with the cohomology generators, because cohomology is dual to homologies cycles. And when you do this expansion, I know T4 is the generator for the Z2 torsional group of this cohomology class. Now A1 is a Z2 field in 3D. So if I start with F5 star or something like that, Yeah, this is not a good example actually, but it's fine. But yeah, after you do this, I mean, it's because of in the C3 case, you have this action in 10D. This will give rise to something like this. So this will give you the transimus theory in 3D. And you can think of some other case that, oh, I might have some 3-form flux whose dual or wedge term is, G3 wedge G7 is its Hodge dual, this kinetic term. Then after do similar thing, you can uplift this to differential cohomology and write down and expand it in terms of the cohomology generators. Then you end up with some theory, let's say A delta B. If you expand this as G3 equal to, I don't know, A star T2, I guess. So if H upper 2 cohomology is a Z2 valued cohomology class, then you know the A field is a Z2 field. And you can expand G7 into the dual cycles of these T2 generators, and then you end up with a Z2 gauge theory in 3D.
I see.
So this is how you see what is the gauge symmetry in 3D come from? It's just it's come from the cohomology generator of the internal geometry.
I see. Okay,
and
that's okay.
Yeah. And for the isometry case you mentioned, I think is more like so here is that here I just consider the case that branes is the source of the defect or symmetry operators. So I just focus on the flux which is sourced by the branes, and then I do dimensional reduction. There are some cases that the low dimensional QFT had some symmetry. It's not coming from the branes, but it's coming from isometry of the internal geometry. In those cases, you have to turn on the background field for the isometry of internal symmetry and then do dimensional reduction. In that case, yes, sometimes isometry can also become, Z2 or Z4 gauge symmetry in the low dimensional TFT. Yeah, it depends on what kind of symmetry or what's your setup is. Sometimes the isometries, sometimes the symmetry from isometry in one string theory regime will become symmetry from the branes in another string theory regime. Let's say type 2A, it's isometry. Then in type 2B, it comes from some branes. Yeah.
Okay, that's very cool. But yeah, it's a lot. Makes sense though. Are there other questions or from people?
Is there any where do continuous symmetries fit in the story? So for those, I think we don't have SymTFTs, right?
Yes, but you can still write down continuous symmetry from brane. Like the branes wrapping non-torsional cycle will give you continuous symmetries. So back to this picture. So here I'm focusing on the case one branes wrapping on torsional cycles because torsional generators are just Z2, Z3, Z4. So it will become discrete symmetries. But you can also think of branes wrapping on non-torsional cycles. Then the branes in this direction will become the charge defect under, let's say, U1 symmetries. But the symmetry operator from branes is quite non-trivial. It's not from some common branes. It will from some flux branes. It has one dimensional higher than Euro-D branes. That's how you build the linking for the U1 symmetries. But yes, you can build symmetry. You can build continuous. You can build a continuous symmetry defect and a symmetry operator from that point of view. But yeah, there's no SymTFT there. But you can still, but you can still see the mixed anomalies between continuous symmetries and the discrete symmetries because you know the linking between non-torsional cycle and the torsional cycles. Those will give you the mixed anomaly coefficient in the dimensional reduction.
I see. Yeah, cool.
Yeah.
Thank you.
Yeah, thank you for asking.
Okay, well, barring any other further questions, let's thank our speaker again.
Thanks.
Okay.
Actually, I thought of one more question.
Yeah, sure.
A further question.
No problem.
Which is what about non-invertible symmetries?
Great. Non-invertible symmetry also come from brains. So usually, okay, let me give you one example. So usually from okay, so for D3 brains, right? I mean, actually for any P brain, okay, for any P brain, there is a very natural topological sector of that brain, which is come from West-Domino terms. CP plus 1 plus CP minus 1, but B2 minus F2 plus CP minus 2, sorry, CP minus 3. Yeah, it's actually exponential, but let me just write it in this way. So for every P brains, which has P plus 1 dimensional spacetime, it's not only coupled to its electrically sourced form, but it also induces any lower dimensional brains charge. If you only focus on this part and do dimensional reduction, you will have invertible symmetry operator. The invertible symmetry operator comes from taking into account all these terms. This F2 is the field strength of the gauge field on the brain's dynamic, on the brain word volume. So for a D brain, right, it can couple to some supergravity flux, but it also has its own physical degrees of freedom or propagating degrees of freedom based on the open strings fluctuating on the brain. So this is the, yeah, so this is the dynamical degrees of freedom on brain, which you should path integrate over. And it's because of these extra terms you build non-invertible symmetry operators. Is that clear?
I think I have to think about it some, but the idea is there. Thank you.
Yeah, right. Yeah. It's basically if you focus on the leading order term of the brains, then it will be some invertible symmetry operator under dimensional reduction. But if you think of sub-leading terms, which you take into account the localized dynamical degrees of freedom, which has to be path integrated over, then that will give you non-invertible TFT on the deep brain word volume. And that is responsible for the non-invertibility of the things. Like in the field theory perspective, right? We know like the work by Shu Heng et al. They say that, oh, I start with some invertible symmetry, but then I realize it's not gauge invariant or something like that. Then I build some quantum Hall effect action, which it has its own localized U1 degrees of freedom, right? And you path integrate over that. You pass integral over that thing which makes it non-invertible, which makes this operator non-invertible. This is exactly the same. You have exponential of this thing, and you have to integrate over this F2 or A1.
Do you only get condensation defects doing this?
No, not it's depends on the setup. You can have Kramer-Weiner types line there. You can also have condensation defect. It's based on your setup.
I see. I guess it depends if this action has a
right. Yeah, exactly. Yeah. So in my recent single author paper, I built this Kramer-Weiner or Tambura Yamagami D2 times D2 Tambura Yamagami lines from D5 brains, D1 brains, and D3 brains. There are also some works by Jonathan and other people. They find that the D3 brain can build condensation defect in 60 SymTFTs. And there are all kinds of things. So it's based on the setup you take from string theory. It's based on what kind of brain you take. You can have, I would say, all kinds of non-invertible symmetries. Yeah.
Very nice. Thank you.
Yeah. Thank you.
Okay. Thanks again. I'm going to end the recording.